Hi, thanks. So I'm Alex Bradbury. I'm a co-founder of the lowRISC project, and I'll say a little bit more about exactly what we're trying to do. But today I'm talking about the LLVM, one of the software components of our work. So first of all, I wanted to say a little bit about what is LLVM and why you, the kind of RISC-V community, might be interested. And a kind of a useful starting point is actually to look at what LLVM isn't, as there are a number of very common misconceptions that I kind of like to nip in the bud. The first one is kind of a mistake that goes back to its initial naming. It is not a low-level virtual machine. LLVM, the LLVM acronym no longer expands to that. LLVM is just LLVM. And kind of related to that, it's not a target-independent representation. You can't take your LLVM IR that may have been generated for targeting ARM and then just run it through and have it run on RISC-V. There are very interesting projects that are looking at doing that, like recently the LLVM work, Pinnacle, and other related efforts. But that isn't LLVM itself. It's also not a C compiler, although the wider LLVM project does include Clang, which is a high-quality, mature C and C++ compiler. It's also not some kind of magic go faster pixie dust that you add to your project or solve your engineering problem, and all of a sudden things are 100 times faster and we're all happy and we can go home. But it is a very high-quality piece of tooling that has widespread adoption across industry and academia. It's a permissively licensed compiler infrastructure. It's home to, as well as the kind of the core LLVM infrastructure, so the code generation framework. It's become home to a number of closely related projects. Initially, it was just LLVM and Clang. Now there's rapid development of LLD, which is a permissively licensed and efficient linker, the LLVM debugger, low-level runtime libraries like compiler-RT or the C++ library, libc++. And one aspect that's certainly quite interesting, given that we already have other C compilers, there's lots of reasons you might be interested in having this particular LLVM and Clang, but also there's all these interesting new languages such as Rust or Julia or Swift and various others, Pony, that have LLVM as their native code generation backend. And so LLVM is a route to supporting those languages on RISC-V or indeed any other architecture you might be interested in. And so why is this something that lowRISC is doing? Or why are we interested in pushing this forward? So, I mean, from yesterday, it seemed like there were quite a few people who haven't been to a previous workshop. So we've been talking about our work kind of from the start of RISC, since RISC-V was publicly announced. So lowRISC is to give a bit of background, we're a not-for-profit project established about 2 years ago. We're established as, what's in the UK, we have a community interest company, and what that means is that we're we're set up to benefit a defined community. And for us, that's the community of anybody who is interested in or who might benefit from open source hardware, whether that's hobbyists, academics, startups, or established companies, kind of regardless of of who you work for or whether you're currently sponsoring our development or not. Our mission is to try and help you adopt and make use of open source hardware and kind of build the stack around that you need to work productively. And so our initial aim was very much to bring the benefits that we enjoy in the open source software world to hardware. And the specific way we've been going about doing this is by producing a complete SoC platform for others to build upon. Something that's multi-core, Linux capable, 64-bit, and also has some novel features I'll briefly touch on, which kind of feeds into why we're interested in software stack work. And so we kind of look at this as being Linux of the hardware world, where we have a base platform that you can copy and paste and then adapt and modify to your needs. And kind of the way we're set up is building from our experiences with Raspberry Pi, which also came from our group, is we rather than kind of cheerleading from the sidelines or writing long, interesting essays about why we think open source is great, we think that the best way of achieving our mission is to actually get in there and do it by doing the engineering and research that's required to build this platform, ship it out to end users, and hopefully get adoption from some of these communities who I mentioned, hobbyists, academics, startups, more established companies. And so two of the focuses for our work have been on both security and flexibility. So with security, we have support for tagged memory, which I won't go into much detail at all here. I've talked about it at previous workshops. But essentially, you're associating some small amount of metadata tags with each memory location. And if this can be used for fine-grained memory protection as a mitigation against control flow hijacking attacks. But we're also interested in a variety of other uses. We have a kind of memo up on our website that goes through the various ways that we're pursuing tagged memory. And of course, this is a great example of something that needs compiler and software support for both a full evaluation, but also when we want people to adopt our platform and have end users who are able to grab their piece of software and recompile it with support for these kind of features. Similarly with Minion cores, which is for us what we call our small microcontroller class cores, which we integrate alongside our main Linux-capable application cores. And the initial motivation here was for programmable I/O, so it's kind of software implementation with some small amount of hardware support for SPI, I2C, I2S, and so on and so forth. But there's also a wide range of other tasks that we're interested in using it for. I think secure isolated execution is a particularly interesting one, some kind of open alternative to the solution that various other vendors end up at, like the Intel Management Engine being a common one that was alluded to talked about yesterday. And over the kind of long term, we're interested in kind of distributing these small cores throughout the SoC, seeing how much of the fixed logic we can move to something that's programmable with software. And a key part of that is obviously meeting area power requirements, and that will involve evaluating new instruction set extensions to further specialize these cores. And so our Minion cores at the moment, we're integrating them based on the Pulpino work that you heard about yesterday. And so that's kind of why we're very interested in compiler work. Obviously, we're producing this hardware platform. We need a software stack to support it, and something that we can use to further our research and development goals. And so looking at the best way of going about this, I decided there are a few goals with what I want to achieve with a RISC-V LLVM backend. So I think there's a huge opportunity that I've been working on for RISC-V to act as the reference backend for LLVM. RISC-V is importantly open source, modern, very clean, all the reasons that we like it. So it's an ideal candidate for being the kind of textbook example of how you write an LLVM backend. And this is useful both for the upstream LLVM community, but incredibly useful for all the groups who are kind of trying to explore new extensions to RISC-V, who are working on or evaluating new proposals. I think obviously documentation is clearly part of that. And again, the next two the bullet points kind of go together. It's important that this work is developed upstream and integrated into upstream LLVM, so we benefit from LLVM code review process, our release management. We don't have to keep rebase. We don't live in our own kind of little isolated worlds. We want this to be shipped out there to end users. And so an important part of that is to kind of split it up into clean incremental patches that build upon each other so that it can be reviewed by other LLVM developers and kind of work in that process. And so in order to achieve all of these aims, that's kind of why I started with a fresh implementation, taking inspiration from a wide variety of other backends, kind of with these goals in mind. And so I kind of mentioned some of the justifications for this on the previous slide. Most importantly, and most interestingly for me, we talk in the RISC-V community about when we have any kind of proposal for an extension, that this should come with an implementation. And obviously that shouldn't just be a hardware implementation, it should be the software support as well to really kind of complete the story, close the loop, ensure that the proposal that's under discussion actually meets requirements, doesn't have any hidden defects. And so this is kind of an important step to making it easier for people to do those kind of evaluations, for lowering the barrier of people who are doing interesting kind of hardware, software, co-design to do the compiler work that's necessary, where often and kind of somewhat needlessly, it can be quite difficult, partly due to the fact that LLVM backend design can be a little bit of a kind of dark art. They're often written once, and then very few people who work on the kind of backend stages. There's much more work and more documentation for IR to IR transformations. And so supporting RISC-V and low-risk education research is an important part of this. And I think, fundamentally, if RISC-V is the way that RISC-V is going, seeing all of you at this workshop and the growing number of people across the last 2 years, is that inevitably RISC-V will be the 32-bit and 64-bit architecture with the widest variety and diversity of implementations versus any other 32-bit or 64-bit architecture. And I think this puts a somewhat unique pressure on kind of the quality of our core tooling. It means there'll be a much wider, greater number of individual vendors who are supporting their own instruction set extensions, who are supporting their own kind of long-term compiler releases. And obviously, yes, I want everybody to, wherever feasible, to work upstream and work from kind of core maintained tooling. But inevitably, due to business requirements or because it is kind of internal research project and something that's not going to be, or a research project that might go for a few years and then it either will be, a proposal might be made or it might not, there'll be all sorts of cases where people are maintaining something out of tree. And so that means that there's a lot to be gained by ensuring that that core work is as clean, well documented, and easily accessible as possible. And so I've been working with LLVM for a long time, the past kind of 6 or 7 years. I've developed and implemented and maintained an LLVM backend for a research architecture that would have been a hell of a lot easier if RISC-V had kind of existed 6 years ago. And so I kind of drawn on that experience and talking to other LLVM backend maintainers to try and go about this in the kind of most sensible way. So I built from the machine code layer up, and this is kind of going from kind of enough support to go from assembly to machine code, which can actually be quite fiddly to add after the fact. I think it's quite a useful way to go about implementing an LLVM backend. I think there's a very, very common trap that is really easy to fall into, because that as I said, there's relatively little documentation. So you go and you look at how other backends are implemented. You find some code that does roughly what you want, or you look at MSP 430 or Spark and you kind of copy and paste some implementations there. And it's really, really easy. Let's say that you copy the implementation for lowering a call. You see it has all these special cases and all this stuff handled, and then you try and fix it up there and then so that it works for your platform. But actually, this tends to lead to code paths that aren't properly tested. So the approach I've been taking is to work very incrementally, adding detailed test cases. So I'll start with implementing, say, call lowering, but initially it won't support all the tail calls, var args, all sorts of corner cases about stack frame lowering. It's much, much easier if you bail out when you can't handle something to then go and find the source of that assertion than to try and work out where in where your kind of code generation is going wrong. And it's kind of obvious software engineering, but it's just such an easy trap to fall into given the way that we tend to develop backends. And so I'm going to give an incredibly brief whirlwind kind of insight into some aspects of LLVM internals, just so you have an idea of what I'm working with. So we're going to start with something that hopefully many of you are familiar with. So this is a basic, incredibly trivial kind of toy RISC-V example. A contrived example, RISC-V 32, assuming a static code model. So all I'm doing is I'm loading two globals, adding them together and returning them. And of course, if I was writing this manually, I might decide to make use of some assembly mnemonics to make it a little bit easier. And so I said I started with machine code layer. So that is how you go from this down to kind of encoded instructions. And so this is what the kind of internal representation looks like. And you have to and LLVM gives you the infrastructure to help deal with all the kind of questions of, we have this %i thing, how should that be interpreted? How does that then get translated to an ELF relocation? Or error checking for when I use certain immediates so they don't overflow the bounds of my signed 11-bit immediates, and et cetera, et cetera. And then, so that's kind of, we've gone from assembly to encoded instruction, but then there's the step above that. There's perhaps a more interesting step, as writing assembly is not all that hard, and that's going from the intermediate representation. So once we've gone through, say, our C compiler, and gone through various optimization stages, we end up with a intermediate representation, which we then want to translate to RISC-V. So how do we get from? So here I have roughly the example I just showed you in LLVM IR. And so how we translate between the two is we have an instruction lowering stage. So this is where we iteratively replace generic instructions. So here these lowercase load, add, and there's a few already. There are a few kind of more specialized target-dependent instructions with the target-dependent assembly instructions. And so we go through the process of instruction lowering, we go from this to something that starts to look a little bit more like RISC-V assembly. So we can see that we have an add, an add-I, load word, LUI, and there's obviously a very obvious candidate for peephole optimization here, as the add and the load are kind of redundant together. And all this is done through a sequence of patterns specified in the domain-specific language I'll mention next. And then finally we end up with machine instruction, where the lowering to actually encoded instructions is kind of straightforward. So this is a very simple example of, we have a RISC-V backend. We want to try out a new instruction. This is the simplest possible case of adding a new instruction, seeing how it works. So the count leading zeros, this is kind of implemented in a table gen, which is a domain-specific language used throughout LLVM. This is kind of stuff that's, let's say, I've already written. So the definition of a R format RISC-V instruction, and in this simplest possible case, you just need kind of 1 or 2 lines to specify the various opcode parameters that you're using, and here the pattern that's used for instruction selection. And as I say, this is the very kind of simplest possible case because there's no need for custom lowering or matching or various other things. As you can imagine, once you start to add more complex instructions, you then have to kind of delve into C++ and add new relocation types or custom matching. And so where am I at with RISC-V and LLVM so far? So this is something I've been doing in a kind of upstream way. If you follow the other work I do in the LLVM community, like LLVM Weekly, you'll see, I posted out an initial series of machine code layer patches for review. The majority of those have been reviewed, accepted, and applied upstream. The kind of next step is the initial code gen support, which I've been working on recently and is very almost ready for kind of cleaning up and public review. The way I kind of tend to work is that I have a local tree with lots of somewhat messy patches. I'll try one thing, I'll try something else, and then I kind of regularly rebase that and then merge and clean it up so we have a very clean, logical set of patches for public review. I think the kind of most important next major milestone for me is mid-January. So when there's, I think by then we should have enough code generation for a reasonable portion of what GCC calls their torture suite, which is a fairly large corpus of fairly straightforward C programs. And obviously there'll be a large number of failures, but at that point we should have I think there'll be a point where development can be more easily parallelized. So we might find that there's all kind of issues with a floating point calling convention or handling structs in var args, in var arg functions, but it's the kind of the base stuff is there. And the kind of long-term roadmap for my work kind of depends on future funding and the level of external participation. So if it is something you're interested in supporting, or applying this same philosophy to other projects in the RISC-V software stack, then I'd love to talk to you. So I think there's a number of ways that we can kind of use this work to improve upstream LLVM, which I think is important. I think if you look at open source as just something that you can take from and you'd never invest in actually improving it, then you're kind of missing the whole point and missing kind of the opportunities that are available to you. So clearly the reference documentation and tutorials is a useful contribution. I've been discussing with Christoph Parsek, who's the maintainer for the Hexagon backend, and we've been talking about a proposal for supporting essentially an abstraction that would reduce code duplication for RISC-V, PowerPC, MIPS, Spark, all these ISAs where due to some engineering decisions in LLVM, you end up having to duplicate all of your instruction definitions across, you duplicate some of your instruction set definitions across 32-bit and 64-bit. And of course, that's a little bit worse for us in RISC-V when we start talking about RV128. I think some of the work I've done on, so I mentioned that there are some cases where you kind of copy and paste code writing an LLVM backend. I suspect, and it's something I'll have to do once I've completed the LLVM backend and then really go through, I suspect there's an opportunity for extracting out more code than is currently extracted out as something that's reusable amongst LLVM backend. So something not dissimilar to, if any of you are Linux kernel hackers, like the ASM generic infrastructure, where if I'm writing a new Linux kernel port and my architecture doesn't need a special Futex implementation, I can just import the standard one. And I think there are a number of cases where we could provide some infrastructure to support that kind of thing in LLVM. Now, for the wider RISC-V community, as I mentioned before, it's really important that we test the hypothesis for all the extensions we're discussing. Now, we need bitwise manipulation instructions, yes. Somebody has a specific concrete implementation, that's great. Then we need to actually test that with real code and compiler support and so on and so forth. I think there's a really interesting opportunity with vector ISA, so the work Chris was talking about, which is really exciting, where viewing how other ISA vendors tend to work, often it's very much kind of thrown over the wall. Like a specification is written, and it will have been written with some internal compiler developer support, and then it's thrown out there. This is spec v1.0. Do what you can with it. Maybe the compiler writers will complain, and they'll have a 1.1 or a 2.0, and it'll be fixed later. But there's a real opportunity to do better than that in the RISC-V ecosystem, to really pull in the experienced compiler developers who have been banging their heads against the wall about weird decisions made on whatever ISA it is they're targeting, and kind of gain from that experience. And so the previous RISC-V workshops, I gave an update on our wider low-risk goals. So I'll just give a very brief update now. Our next major target is around the end of February. We have a sequence of code releases with detailed documentation you can find at our website, which recently got a little bit prettier than it was before. But our next target for a code release is kind of end of February, featuring our Rocket core-based multi-application cores, a optimized tag cache, so something that's further optimized than what we previously talked about and released, as well as the initial integration of the Pulpino-based Minion cores. So once we have all that together, that gives a kind of complete base to iterate on. There'll be various things that we want to errata or things we want to fix up before we actually tape out, but it'll start to look like our final V1 SoC platform. And we're expecting to launch a kind of crowdfunding campaign or similar for the initial instantiation of our platform. So that's 64-bit, multi-core, Linux-capable, fully open source, RISC-V SoC with Minion cores, tagged memory, and so on. So in conclusion, if you want to get involved, please talk to me. Take part in the code reviews on upstream LLVM. So the LLVM Fabricator, the LLVM mailing list, and I run a summary of the LLVM mailing list that should give a useful summary of ongoing discussion if you want to kind of see what's going on there. One thing that I really would like to highlight is the recent effort to generate a RISC-V ELF PSABI document, which is incredibly important for LLVM, GCC, but a whole host of other low-level RISC-V software. And it could really benefit from people who have had experience with the mistakes or perhaps questionable decisions made in previous PSABI documents on other architectures. And in general, it would just be really good to kind of flesh that out so we have a solid base. So I think with that, I will, are there any questions? Thank you.
Rishi or Nikhil from BlueSpec. So could you, the LLVM work takes into account what you're doing with tag memory also, or is that just a separate thing?
So it is the prerequisite for the tag memory work that we want to do. So it does not currently integrate tag memory support, but once it reaches an appropriate level of maturity, then that's something we want to use it for.
So in the meanwhile, how do you access tag? Is it just special instructions that you insert in, or?
Yes. Yeah.
Anybody else? All righty.
Great. Thanks very much. Thank you.
Thanks, Alex.